All right, greetings. It's March 22nd, 2023. We're in Cohort 3 and Meeting 9 in our second discussion on Chapter 4 of the textbook. So last time we went through some sections and we have also a lot of questions that have been addressed. So, before we go back to the text or to the questions, does anyone who's here want to just give any thought or reflection? Yeah, what are you still looking to reduce your uncertainty on? Or what
I'm
do you
I, I'm just finding, yeah, I'm just finding a lot of the mathematics. Um, it's just not explained in a way that disambiguates what a particular expression might be. Um, I've got certain uncertainties about some of the mathematical objects themselves. Um, and then particularly on the section on Taylor series, and I feel that I have a pretty good grasp on Taylor series. Um, that's feeling particularly opaque to me, which feels surprising. Um, yeah, I'm finding it a slightly frustrating chapter, which sort of dives into the maths, but in some sense without enough detail for me to really deeply understand it. But maybe that's just a matter of time.
Thank you. Well, definitely when building on a sort of meat and potatoes mathematical concept, someone with your expertise should not be overly confused. It should feel like you have already been on the on ramp to understanding where this is going, because it's hard to imagine it'd be clearer for someone who is less familiar with the foundational pieces. So let's definitely keep that in mind when we move through. Okay. Um, Anyone else want to just give any o- overview thought on a section of 4 or anything else on how they're thinking about any aspect of it since last week? Then we will look at the questions and then continue to move through the text. I'm just looking at the previous video to see where we ended. 410. Okay? Any other comments? Otherwise, we're going to go to 410 and continue, or a little bit before. Okay. All right. Let's pull back to 4-4 and just please raise your hand or write in the chat with any thoughts or questions. So just looking at the questions that were submitted in this cohort, many of them involve the equations 4, 7, 8, 10, and so on. So these are ones where we can look at what was written for those where things were written, or otherwise just kind of given the constraints on what we can do in 50 minutes, just recognize these are important areas for there to be asynchronous development on. But this looks like a great answer, whomever has written this, and it's like an exemplar of how to address it asynchronously. Yes, Jonathan?
Yeah, so this was my contribution here. The explanation underneath. Um, I still have some questions about it, despite the fact that I think I now understand the sort of the vector aspect. So I've created an overleaf document that sort of explains all of this. Um, I'm still slightly confused by something quite simple here in the expected free energy, because there are these tau indices floating around, and tau indicates, I think, the time, the moment in time. So, for instance, S of p subscript pi tau is the probability of being in a given state um, at a particular time, given that you're undertaking some policy pi. Um, and so there's a tau index floating around, but it's still not quite clear to me in the calculation of the expected free energy um, what you do with that tau index. Are you summing over all of these terms? Are you integrating over them? It is an expectation value over all of the different time steps. So that was the one thing that was sort of least clear to me here.
Yes, great point. Is it expected free energy as an expectation of snapshot free energies? Is it a expected free energy as the sum of the expected futures? Or is it even the expectation at that last time step alone?
Mhm.
And the other ones are discarded. Good points. In figure 4.3, we have the discrete time, partially observable Markov decision process, POMDP, and the continuous time cousin. In the discrete time case, past, present, and future time steps, hidden states are explicitly predicted, and action sequences are explicitly intervening in how hidden states change through time. In contrast, in the continuous time model, rather than predicting or even explicitly mentioning past, present, and future, we see like x, x prime, x double prime, so the value of x, and then the higher derivatives, also known as the generalized coordinates of motion. And so this amounts to making a Taylor series expansion, which is continuous, around the current time step. Two different ways of dealing with temporal depth and the way that action selection relates to temporal depth. And they have some, in principle and in practices, strengths and weaknesses in different settings. In 4.4, they're going to focus on the discrete time model. The discrete time model has been especially applied to categorical cognitive decision making, whereas the archetypal case for the continuous time generative model is continuous perception and action of like a motor unit. And they can play well together, as we'll see in chapter 8 with hybrid models. We could go slower, fast on equations, but we'll just try to like move through the whole thing. But many of these, the work to be done is making sure that we have high quality descriptions verbally, which we do for many, due to many people's great work, but making sure that we have verbal descriptions in the active inference ontology that are faithful to the symbols. And then where people have questions about what does this mean? Why is that way? What if it were this way? What are the implications here? Those are all great questions, and they can all be included in the notes section for a given equation or in the more general notes table. But for many of the equations, including some of the super challenging ones, we have things written out, which is very good. But just kind of at the skim level, cat is a categorical distribution. So in this section, we're in a discrete setting. So like the light is on or off. The continuous setting would be it's a continuous variable between 0 and 1. But in the categorical setting, we have categorical distributions. And so we have certain ways of summing across them. For example, instead of taking an integral over a continuous distribution. Action selection, pi, policy selection, is going to be guided by which policies are most likely, most self-consistent, most self-evident, most probable, lowest expected free energy. We're not proposing a reward or utility function and then evaluating policies based upon their expected reward. We're evaluating policies based upon their self-consistency, and in fact, the most probable ones are the ones that lead to the lowest expected free energy. So, more equations. G is expected free energy, and even just looking at which variables go into this, we see a probability distribution over policies that is defined through an expected free energy calculation. And this G of pi, it's a function of policy, and it is going to have this expected free energy construction. And we've seen expected free energy before in equation 2.6, where the part that's an expectation that only involves preferences and observations is pragmatic value. So, natural log of a distribution, expectation of a log of something only involving observations and preferences. Here we have y tilde. Here we have o tilde. Y is sometimes used for observations more in like a linear regression setting. O is like observations, but they're identical. And then the other component is and so it's pragmatic value because that is the alignment between the observations and the preferences or expectations. The other component in this decomposition of expected free energy is a KL divergence, expected KL divergence between two variational distributions, two distributions that we control, Q. They're both X, hidden states through time, X tilde, conditioned upon, and then they're very similar. Here we only have pi. Here we have pi and y. So this is the divergence with respect to whether adding observations updates our prior. If these two Q's are the same, that's equivalent to saying there's no space between the distributions where we've parameterized X with or without getting any observations. In other words, the observations were valueless if the divergence here is 0. Whereas if the observations are really impactful on moving the distribution, then this KL divergence is going to be big. Divergences are always non-zero. And then there's a negative here. So the more information gain, the bigger the KL divergence, the more that the observations matter, the more that this first term is going to go negative. And so that specific policy will have a higher epistemic value. Ollie?
Yeah, I just remembered a clarification made by Ryan Smith in one of his lectures about two concepts of, or rather two notions of time used in active inference literature, one of which is denoted by tau and the other one is denoted by t. So tau is used for the time about which we have a belief. And the examples he gives is, for instance, I believe I am now in my car. So that would be S of tau. But I believe I was in my kitchen 10 minutes ago would be S tau minus 1. Or I believe I will be at work in 20 minutes or something would be S tau plus 1. But on the other hand, we have T, which refers to the time at which a new observation is given. So, for instance, as an example, after turning on a light, I now, in other words, S of tau, believe that I was in the kitchen for the last 5 minutes, right? So we can update our belief about all taus or S of taus with each new observation at each t's or at each given observation times. So briefly, one is the belief time and the other one is the observation time. So tau is used for belief times or the time about which we have belief, and t is used for observation times.
Thanks. That's very helpful. Is it accurate to say that T is like the click of our simulation that's actually handing the new observations in at a given moment, T after T, but then especially in sophisticated active inference where we might be considering like the past, present, and future at every T, we are reevaluating taus at each T.
Yeah, I think we can reframe that in this way as well.
Awesome. So here we reach, yes, potentially with some bumps and jumps, the expected free energy for a policy in terms of the pragmatic value, alignment of preferences with observations, and the expected information gain, the epistemic value, in terms of how much adding in observations updates our variational distribution about hidden states conditioned upon that policy. Here is more focus on how we get this KL divergence. So here we see that KL divergence, and there's just a few different expansions and relationships around it. Jonathan?
Yeah, so just zooming into that equation there, there's an expectation over Q of O given pi. And I couldn't figure out how that's calculated, because I understand how one can get Q of S given O and pi, but it seems that to calculate Q of O given pi, one needs to marginalize or sum over the states. And I thought that was the whole reason for introducing Q in the first place, was because we can't sum over all external states.
The subscript notation may be used in an unconventional way, but I agree with you on that. Here in the inner Q, we have it about S, conditioned upon observations and policies. This doesn't seem contentious.
Yeah, that's fine.
Yeah, but the subscript, in 4.8, and I think that was probably one of your questions.
Yeah.
Yeah. Yeah.
Yeah, that's the one. Sorry, with the terrible lack of
Yeah.
Sorry.
Yeah. Yeah, we should look at the MATLAB code for wherever that comes into play to see how it actually is done. Or is it a separate variational quality? Yeah, like this is just the inner value is the KL divergence of how much observations update add in to your changing beliefs about S. But we're taking an expectation of that over expected observation sequences, which then begs the question of needing to know the distribution of S that would generate those probabilistic envelopes of O.
Exactly.
Yeah. Well, one answer is these are the analytical ideals for which there are strong analytical guarantees, and then any given computational implementation is going to use different methods to implement this just procedurally. But that doesn't make the notation clear. And I think these are some of the kinds of artifacts, hopefully cohort after cohort, we can craft, like a lookup table. And we've done this to a limited extent, just starting it. But having a lookup tables for all the different shapes and squiggles. But continuing on, so I hope that we can at least see the rest of it. Variational free energy F and expected free energy G. Variational free energy, which we'll recall from equation 2.5, is a functional of Q, the distribution we control, and Y, the incoming data. So variational free energy is like the real-time unfolding model fit. And this is a quantity that's widely used in statistics. Expected free energy uses similar structure and positioning, but it explicitly brings in two pieces that aren't present in variational free energy. And those are observations, which haven't happened yet, because we need to talk about how informative we expect observations that haven't occurred yet to be. Information gain, epistemic value. Obviously, variational free energy is only concerned with the actual data point being acquired at the moment. And then secondly, the fact that we can take different policy choices. And policy choices end up conditioning, for example, what pragmatic and epistemic value we achieve or expect to achieve. So, free energy can have a variational free energy formulation, real-time unfolding model adequacy. Or projecting free energy into the expected future, we need to invoke observations that haven't happened yet and our agency in selecting alternative policies, which then, of course, bear on the epistemic and pragmatic value we accomplish. Here in 4.9, there are more decompositions of expected free energy that help see previously recognized dialectics or decompositions or trade-offs as actually decompositions of the unified imperative expected free energy. So epistemic and pragmatic value decomposition and an ambiguity plus risk. And one can kind of walk through and see what those mean or look at the natural language. We can rewrite 4-7 in linear algebraic form. Here's 4-7. Here is, for the categorical distribution, we can sum over policies about the policies and the hidden states through time. More details and calculations of variational free energy. Factorization and the mean field approximation. These are some mathematical technicalities, but they are simplifying assumptions or ways to approach this in the general case. This factorization is one of many possibilities in variational inference. And as we talked about last time, variational inference is just one way to do these calculations and represents the simplest option. And in practice, it's nuanced slightly, and there's like other approximations, and it's a whole thing. More information on the letters that we know and love. A, the tale of two densities. B, how hidden states change through time. C, prior beliefs about observations, which are preferences. And the simple prior on the initial state to kick the hidden state chain off. Little bit of policy and belief updating, few more technical details. Into active inference in continuous time. Box 4.1 on Markov blankets. A Markov blanket for a given variable. With just those words, the map territory question is addressed. Markov blankets are about variables. Comprises a subset of those that interact with it. If we know everything about the subset, knowledge of anything outside the subset does not increase our knowledge of the variable of interest. There are several Bayesian message passing schemes expounded on a lot further in other work with Friston, Parr, DeVries, et al. Probably not the most relevant to delve into right now, but the important takeaway is that by using a Bayes graph, so by making a commitment to the figure 4.3 Lego set, if we choose to have nodes be random variables and edges reflect relationships amongst variables in a certain way, then we gain access to message passing techniques that make even large Bayesian graphs with different parts of the graph updating at different speeds and so on. There are software packages that are able to, in a defined computational complexity setting, run inference on those Bayes graphs. So yes, bigger models, all things being equal, take more time and more computational resources to run. However, there are some tremendously scalable, high-performance ways to computationally implement computation on these graphs. And they have interesting analytical representations, and they have a growing set of toolkits like reactive message passing.jl by the Bias Lab with Bert DeVries and his lab. This is like really cool current work that's not even outside of their lab and colleagues, not heavily used in even active inference publications, but they have incredible recent work. And you can see how they're using variational free energy in these advanced settings. Pulling back to consider message passing qualitatively in the chapter, whereas it was introduced in this Markov blanket box, message passing, though I'd be totally looking, oh, thank you, I will, yeah, there's the Bias Lab site, and I'll add it to the figure 4. The reactive message passing is like one of their new pieces where, let's say you had 2 sensors and one of them was being updated every second and one was being updated every hour. Well, if you only could turn the clock, if you might get into a situation where you were either say, well, should I update my model every second and then oversample the slow variable? Or should I sample my model every hour and undersample the fast variable? And reactive message passing navigates that by actually having nodes update on demand. So you can have one node that's just getting pinged every second and another node that's getting updated on a different time scale, and the computation's on demand. So that allows you to have like lifelong online learning for Bayes graphs flexibly with different rates of sensors. And so those are the kinds of toolkits like these models are not just being proposed to promote theoretical unity in the cybernetic sciences. Also, there are powerful software toolkits that using these kinds of architectures enable. So epistemic value, pragmatic value. Message passing schemes. If anyone has any takeaways from this image, please feel free, because certain things are like omitted. And also it uses like a lot of squiggles and E's and different variables. But here we have a representation of a hierarchical model. So you can tell it's a hierarchical model because you have like I, and you have this kind of cluster of 4, and you have I plus 1. And you have errors getting passed up and hidden state inferences getting passed down. And so this would be like the sort of timeless representation of that modeling hierarchy. Hierarchical Bayes, hierarchical predictive processing architecture, tilde through time. So we're just describing timelessly, here is the hierarchical Bayesian model. This can be rendered or unpacked through time. Now we see that tau minus 1, tau plus 1 as a function of time. So instead of just seeing it as like O tilde, like a sequence, and seeing this as like a skyscraper, this can be unrolled in a procedural way using message passing techniques. Kate, are the rules for message passing on a convoluted Bayesian network known? Yes. This paper that I have just put in the chat, here we see figure 4.3, discrete time. Again and again. And here is a alternative representation of this Bayes graph with what is known as a Forney factor graph. And so in this paper, they show that any Bayes graph can be represented as a Forney factor graph, and any Forney factor graph has a defined procedural message passing algorithm. So actually a quite incredible synthesis, even in this 2017 paper. Because it means if you can build with these Legos, with this semantically interpretable setting, then there will always be a procedural technique to calculate it, no matter how convoluted this graph is, which is very important. Because you could make you could just add linear model layers, but then you would start to lose analytical guarantees very quickly. Here, now we're in the continuous time. So section 4.5 is a lot like 4.4, except it focuses more on the continuous time model. Just to only describe more on 4.15, here we have our observations through time, and that's a function g, little g, not expected free energy. Its observations are being emitted by a function of hidden states and slowly varying causes, v, which kind of plays the role of policy in continuous time, and a noise term. So this is our sensor reading. Here's EEG measurements, SPM measurements, as a function of neural activity and sensor noise. And then the rate of change of neural activity is a function of neural activity at that time and slowly varying causes. So the mapping between data and hidden states, which is kind of analogous to the A matrix, is timeless. And then the rate of change of the hidden states, x dot, which is like x prime, is defined in a certain way. And this is like familiar structurally to those who have looked at physics. Generalized coordinates of motion related to the Taylor series approximation. So the black line is the function, true underlying function. Here's our first pass approximation at this time. Evaluate the function, and then just that's, y equals 4 is this line. Then we have the second term approximation, which is the value 4, I'm just making that up, and then the slope instantaneously. The third order approximation is going to have 3 coordinates of motion: the position, the velocity, slope, and the acceleration. And then if you were to have another term, taking it into another level of exponentiation, you would end up like kind of probably coming back out. So that's how smooth approximation of functions works using the Taylor series, by evaluating higher derivatives around the point of focus. What is the difference between the dot and the dash? Yeah. The x, so in principle, nothing. In principle, they both mean rate of change. Here, x dot and dash are being used because x dot is the change function on hidden states. Neural activity changing through time is x dot. So here is our estimate of neural activity changing through time. Here's the rate of change of neural activity changing through time, x dot prime. But that is not necessarily x double dot. I hope that that's accurate. Jonathan?
Yes, I think one of the things that confused me most here is that we've got an f prime of x prime v prime. So certainly in figure 4.5, the prime really does represent a derivative with respect to tau. And then within the equation here, it's just not quite clear, what one is taking derivatives with respect to and how many times. Like f double prime of x double prime, v double prime. It's
just one,
it's
one does not
confusing.
need these two.
Well, that's what I'm. So to calculate the Taylor series here, you would want to include derivatives, but it's derivatives with respect to the variables inside, like with respect to x.
Yeah.
Yeah. I'm just a bit confused by this.
No, that totally makes sense. I agree. Anywhere where there's a derivative or an integral, there should be clarification of what it's with respect to. And that's sometimes done. But here, prime is being used just to refer to the generalized coordinate of motion at that scale. Okay, then writing down the variational free energy with generalized coordinates. Laplace approximation. This is something where there's a lot of technical detail, but what the Laplace approximation does broadly, also please correct me, is finds the single maximum likelihood estimate for a distribution and then parameterizes a negative quadratic with the point being at the maximum likelihood estimate. So for distributions with a central tendency, Laplace approximation can do really well. For distributions that are bimodal, like with two humps, Laplace approximation is going to identify the slightly taller hump in its maximum a posteriori estimator, and then either draw a pathologically narrow or wide quadratic around the taller hump. Ali? Oh, okay. And more details on that. Quadratic expansion around the posterior mode. Mode, most likely point of a distribution. Quadratic expansion, drawing an upside down parabola around that point. Expanding some of those discussions from the above into hierarchical models. Reviewing the message passing that we saw previously, skyscraper on the left, unrolled through time on the right, in the context of generalized predictive coding schemes. And a short summary. So, definitely an interesting chapter. The mathematical details beyond way back when, basically beyond this point, really escalate fast. And there's also several boxes and asides, like this message passing, generalized coordinates motion, and Laplace approximation, all of which are significant technical concepts. So, a lot of challenges and trade-offs with writing such a chapter, especially because this is like active inference. Chapter 1, overview. Chapter 2, low road. This is how we're going to do it. Chapter 3, high road. This is why we're going to do it. Chapter 4, generative models of active inference. Figure 4.3, discrete and continuous time, generative models. And then there's a lot of technical details. So, anyone have any just overall thoughts or questions on 4? Jonathan, and then anyone else.
Yeah, I think I'd just to get more of a sense of it, I'd still be interested to know more about the tau in G, if anyone has any insight into that. When you calculate G, does G still have a tau index, or is something else happening to it?
Yes, good. good that it is noted. If anyone has a link or thought, go for it. Otherwise, that is definitely something that we will need to revisit and improve for future cohorts. Kate?
Just a very general comment, like this was way over my head overall, but I was just wondering if in your experience, the textbook that you are kind of working through with, I mispronounced his name, Nem Joshi, about the fundamentals of active inference, do you think there will be some help in any of these areas?
Ollie, what's your first thought on that? This is in reference to Sanjeev Nemjoshi's fundamentals textbook that we are like working through and evaluating during 2023. So Ollie, what would you say to Kate's question?
Yeah, in my opinion, I think it is way, way more helpful in understanding the mathematical details and also, in fact, the conceptual intricacies that have been somehow glossed over in this textbook. But on the other hand, it is estimated to be about 600 to 900 pages long. So yeah, it is much more expanded than this textbook, and it goes into a very helpful detail, expanding upon these mathematical derivations. But one point I wanted to make is that Sanjeev's textbook is not strictly geared toward somewhat mathematical derivation of these equations, but its main objective is to use it as a practical tool in order to model these kinds of agents, and in fact, he also provides some helpful Jupyter notebooks in that regard. But yes, I think it can be really helpful in bridging the gap between this textbook and the practical side of doing things.
Yeah, thanks, Ollie. If anybody, so the book is not available yet. It's not even finished in writing. If anybody wants to be added to view chapters and the code, which are all in Python, which also increases the accessibility relative to the MATLAB of this par et al., these chapters, in a way that has not appeared in our space before, are tackling these statistical questions. So it is still like very much an accelerated statistical learning curve. But as Ali mentioned, it's less focused on like, well, here's how you get from here to here as just like as a analytical derivation consideration. And it's a lot more like, we're going to go step by step with building stochastic simulations. And so this is it's going to be a great complement. And fields have many textbooks, so there's not just one right approach. But it's been really encouraging to see his work. So if anybody wants like even just access to the coda to review the chapters, please feel free to email us. And hopefully in the coming year, we'll have more details on when it'll be available. Let us look ahead quickly to Chapter 5. Chapter 5 is the last chapter in the first half of the textbook, which is the epistemic half of the textbook. So, congratulations to those who have continued on, especially through that second half of Chapter 4, which is definitely like intense to a comical degree. And so carefree and whimsical in its writing style, which has its own kind of comedy. But we're going to have 2 weeks on Chapter 5, which is going to be a great return to reality. And then the final meeting will be on feedback, project ideas. Terry, I think we need to approach to the maths pitched at a 7-year-old. Yeah, many angles on that. One is in the math learning group, we've explored these kinds of questions. And another approach is a non-mathematics approach, which several people have investigated. How important will it be if we didn't grasp all the details of chapter 4 when we get to chapter 5? Irrelevant. Chapter 5 picks up on a very different note. Remember that chapter 4, they even said you could skip. Said if you don't want to know the technical details, you can skip chapter 4, which was again like, it was like, wait, but we just took the low road and the high road to our city. And then they're like, you don't have to go on the tour if you don't want to. Chapter 5, message passing and neurobiology. Bayesian message passing comes back. So again, that box that we looked at earlier, the idea that every Bayes graph is sparse. Not everything depends on everything. Because of the sparsity of the Bayes graph, especially, there are some computational procedures that are extremely effective. And, interestingly, real biological systems also have sparse connectivity, whether it's the neural architecture in the brain or whether it's the interaction patterns in an ant colony. In distributed systems, connections are sparse. They begin at the microanatomical level with looking at neurons and their connections. They focus on one of the most well-studied neural tissues, which is the mammalian cortex. And the mammalian cortex has what's called a columnar architecture, which is these 6 histologically distinct layers of tissue. So they look different under a microscope. And the connectivity patterns, in terms of what actually sends axons where, are also essentially completely characterized. And so in here, we see the tantalizingly realist alignment of the histological columnar microarchitecture with Bayesian graphs that have similar structure. In figure 5.2, they're going to generalize and kind of coarse grain the columnar architecture and now look at how different columns communicate laterally. So we have like hierarchical communication within a columnar unit and connections across units. This is kind of like Numenta thousand-brained hypothesis, like a lot of work that is using the neocortical architecture in search of intelligent machines. So that's the neocortex scenario. We're going to switch systems to the mammalian motor cord. Here, we have incoming proprioceptive data, Y, and descending predictions. Those predictions and observations are juxtaposed to form an error signal, which gets passed forward. And so this is a continuous time setting. And here we can see action as resolving discrepancies between target set points and proprioceptive input. Now we switch to another mammalian neuroanatomical system, which is subcortical, and the basal ganglia in particular, which is a dopaminergic region. This region plays a role in policy selection. Check out the Oliver Sacks book or Robin Williams movie Awakenings. It's really interesting and funny. Here we see 2 different ways that the dopaminergic tone tilts the balance towards either action selection, which passes habits forward, or that kind of type 1 indirect policy selection pathway can tip towards a type 2 in a Kahneman sense, deliberative, free energy, updated policy posterior. But we'll talk more about it. They talk about different neurotransmitters in ActInf. They talk about how continuous and discrete models can come together. And then they end the chapter with bringing together those three systems that were previously described: the columnar architecture in the neocortex, the basal ganglia dopaminergic decision-making architectures, and the spinal cord reflex proprioceptive continuous time model. And they show how those kinds of models can be integrated to address some of our favorite topics. So it's a shorter chapter. It doesn't have equations like the previous ones do. So again, congratulations to everybody who made it through the more thick of it, chapter 4. And chapter 5, we're going to have a lot of space for conversations about like neurophysiology and the body. And it's just a good close to the first half of the textbook. So thank you all for joining. See you next week.